1 or 2 minutes until everybody's signed in.
Let me start.
Actually, I distributed the keys to the students, so everybody should have received them and hopefully also installed everything correctly now.
My screen is visible, no? I have shared the correct screen, yes.
Yes, we can see IXCube.
Yeah.
Okay. You have to put some music in the background while we wait.
I think my typing on the keyboard sounds like music, no?
I don't hear that. How is the weather? It's snowing?
Not anymore. We had quite some snow during weekend and beginning of the week, especially in the mountains. I've seen on the glacier it's more than 1 meter of new snow.
Yeah.
But
it's quite cold even here. That's why.
yeah, I mean, this is the time when, at least in the place where I live, we have something like 5 below zero in the morning or during the nights, and 15 above zero during the day. So it's kind of like oscillating up and down 20 degrees.
Yeah, that seems quite okay. Quite cold for me.
Yeah. How is it for you, Ferrichte? Are you freezing? There's two new assistants working with me in Innsbruck, and they're from Iran. So I don't know if they are freezing now, like.
Yeah, sure. For sure, they're not used to Innsbruck.
Yeah.
Well, another week, and then we start getting hot here.
But you're in Naples, right, Jerry? Yeah. But it should be quite warm already, no?
Generally, yeah, but we have quite cold in these days. It's a bit strange. I mean, not so cold, but it's in the morning, 6-7 degrees, and it's cold for us.
Above zero.
Above zero, yeah. We never go under zero.
Okay. So you're never freezing.
we never freeze, but 6 degrees is low for us.
Yeah. Okay. That's where we start to sweat.
We stay almost. We need 20.
Okay. Yeah, that's nice.
Can I ask a question?
Sure.
Yes.
It's about assignment. So I have a lot of study to do in the last 2 days, so I didn't upload my assignment before 6, and it's closed right now that I can't upload.
I know, but maybe you have not seen the. I think I sent a message via my courses saying that we will extend the deadline, because I was waiting for the keys for a couple of days, so not everybody was sending me the keys immediately last Thursday. So I waited until actually Monday, I think. And then in addition, I did a copy-paste mistake. So some of the keys were missing, even a couple of hours longer than that. And then I answered on the my courses that I will just extend the deadline. I didn't do it because I thought everybody will wait anyway. So there is no problem with that. So no worries.
Okay. Okay. Thank you.
Okay, you're welcome. So Terry, I think we can start. I think we are more or less complete. So let's go. Thank you.
Okay. So last time we have seen the two main form finders, the first density method and the natural first density method. Okay. So basically we have seen that using the first density method, we have a net. So we model the membrane with a net of points and connection lines or connection springs, while using the natural first density method or the same, the updated reference strategy, the model is made out of a triangle mesh. A triangle mesh is a mesh made out of triangles. Why triangles? Because a triangle is a flat plane. No? Through 3 points, we have a flat plane. So we model a complex surface out of all these triangle elements. Today, I want to show you another feature. And after this, we will go into Rhino and Grasshopper. But let me start showing you how to model an inflated structure, an inflatable. To make an inflatable, nothing really changes. Everything is almost the same. But we have to make a few steps. Let's make a simple membrane to start with. So I make a new layer, and I call it just CAD drawing. I activate my new layer, and then I enter the CAD tools, and let's draw a simple square. From corners, I just click somewhere here, and then if you want exact dimensions, you can input here in the prompt, or for relative, and let's say 10,10. So we have made the square 10 meters by 10 meters. Now I want to fill this with a mesh. So you select this square. In the FEM tools, we have this tool here called Swan Merge. Swan Merge wants a number of boundary polylines or boundary lines, and working in the current UCS plane, so I am looking from top, he will fill it with a mesh. So we call Swan Merge. It's asking me the size of the mesh. So we have a mesh of 10 meters by 10 meters. One by one, we make a mesh 1 meter by 1 meter. You close with OK, and it generates this mesh here. Now, maybe 1 meter by 1 meter is too big. So we could use the remesh tool if you want to change the mesh sizes. And I want it to be 0.3 by 0.3. So we have changed the mesh size. So we have just a flat mesh here. And now we want to generate an inflatable out of this mesh. To generate an inflatable, we go here into the create new FEB group, and we see that we have the inflatable group. So we just add the new inflatable. Before doing this, remember that we have, if I delete my my polyline, we have a membrane, but we have no edges around the membrane. You must always remember that when we are modeling tensile structures, it's kind of, we are modeling like bubble soaps. You cannot make a bubble soap if you don't put some kind of boundary into the soap, no? We have to put some kind of cable or rigid boundary to have this bubble soap. And exactly the same is in the software. So we need the edges of this mesh. To generate the edges, we can use this tool here, and it's called a boundary, mesh boundary. You click on the mesh boundary, and you see that he shows a dot. One dot means that, look, I have detected one boundary. The boundary will start at this point, will turn around all the mesh, and will close again at this point. And he will make one long chain. Clearly, we do not want only one chain. We would like to have one chain for each edge. So here in the parameters, we have a max angle deviation parameter. If you click on it, you can import an angle. And in degrees, if I input, for example, 60 degrees, you see that now he splits. When he finds an angle bigger than 60 degrees, he generates a point and starts a new edge. So now we have 4 dots at the 4 corners. So you can just click on apply. And we see that he has generated a new group with 4 chains. These are the 4 edges of our mesh. Now, we double click on the edges. These edges are beam elements. They are linear behavior. And then we put them fixed. Fixed means I'm not really interested in the structural behavior. I just want to fix the membrane on these edges. You can input the cross section just to not let the software complain that they have no cross section. So we have generated the edges of this mesh. Now we want to inflate it. Before inflating it, this is quite a big membrane. Later, I want to make a double layer, like a cushion. For this reason, I will double click on the membrane, and I am using now Ctrl+C to copy. So I have made a copy of this mesh. Okay. First of all, we want that this mesh, this membrane, becomes a layer of the inflatable. So you just drag and drop over the inflatable. You see now that the tensor group is child of this inflatable. If we right click on the inflatable and we go into tensor params, we see that the inflatable has detected one chamber. And for this chamber, we have the pressure inside the chamber. In this case, it's 0.25. Remember that we are using kilonewtons and meters. So this is 0.25 kilonewtons per square meter. Okay, this is a pressure. So, okay, let me save this. If you do not save your file, you will not be able to run form finding or analysis, for the simple reason that the software generates a number of scratch files, and he needs to know where to save these files. Okay, so we have saved it. Now we have an internal pressure inside this inflatable. If we double click on the tensor group, this is our membrane. And this is the warp and the weft preset, you remember. We could select the membrane material here. And maybe since this is 10 meters by 10 meters, maybe we need to put a little bit higher preset in the membrane. Now, one question that should come out is, okay, this is the stress in the warp, the prestress in the warp direction, and the prestress in the weft direction. But what is warp and what is weft? I mean, this is a square, and these are triangles. So what is warp and what is weft? We don't know. We have to assign warp and weft. Now, since the default UCS is horizontal, you can right click on the membrane, warp weft mapping, set warp weft orientation. If we recall this tool, this dialog box is asking us to choose the warp weft plane. And we just said the current XZ plane, so the plane that is vertical to this line here, defines the warp plane. You just click with OK. Let's say that we want to see now which is the warp and weft plane. We want to check it. You can go into Plots, Options, Labels, and here we have the object axis. Activating the object axis, you see, let's make them smaller. Okay, you see these axes here, and we see 3 arrows, one red, one green, and one blue. And it's easy to remember. RGB is the color for monitors. No, red, green, blue, RGB, X, Y, Z, warp, weft, and normal vector. So red is the warp direction, green is the weft direction. And we see that we have assigned it that this is warp and this is weft. Okay, let's save. We are ready now, and we can just, let me take off this. We can just recall the form finder. You see here that we have 2 form finding tools. One is called Form Find, and one is called Form Find Stiff. We will see the difference of these two in a few minutes. I will recall Form Find Stiff is asking me how many steps I want to run. 5 is okay. You just run 5 and say okay. And you see that the membrane has been inflated. Let's give a look in shaded mode. We see that it's inflated. And if we go into response, form finding, and we activate the membrane stresses for the warp direction, we don't see anything because the mesh is visible. You go in wireframe and you see the stresses in the membrane. Clearly, what we see is a 3 kilonewtons per meter because we have set up that the mesh has a 3 kilonewtons per meter pre-stress. The same if we choose the Y stresses, again, a 3 kilonewtons per meter pre-stress on the membrane. Okay.
Jerry,
So, yes.
can you maybe explain a bit about, because you mentioned it's 0.25 kilonewton per square meter of internal pressure that you choose.
Yes.
And now you select it instead of 1 and 1 for warp and weft, 3 and 3. So how do you select, and what is internal pressure? So how much is needed for a cushion? I think this is important information for the students.
Exactly. With inflatables, I'm searching for the draw tools. So, okay, if this is inflatable, a balloon. Oh, there is the arrow here. This is the internal pressure. This is the internal pressure P. In any point of the inflatable, we have this pressure that is pushing the surface. Then we have in any point, we have, let me change color here. In the membrane, we have the pre-stress of the membrane. These vectors at each point, the pre-stress is tangent to the surface of the membrane. And this is the pre-stress of the membrane. So clearly, the shape is in balance. The pre-stress of the membrane and the internal pressure is in balance. And this is a famous formula. You can find it. It's the Boyd formula, where there's a relationship between the pre-stress of the membrane and the internal pressure and the radius of the shape. So the radius of the shape, this one, there is a relationship between the pressure P, the radius, and the tension. And now, if I don't make a mistake, if I make a mistake, tell me, because I'm the tension T should be the pressure multiplied the radius divided 2. The pressure multiplied the radius divided 2. Let's see if it's let's check if it's true. Okay. If we get to this, I would like to measure the radius of this. I will get this mesh, Control C, Control V, and I'm in Rhino. You remember that if you're using 7, you have to save. If you're using Rhino 7, you have to go here, File, Export, CAD, and you choose here Rhino. And he will save as a Rhino 6 file. If you're using Rhino 6, you can do a Control C and the Control V. I will join these. And now, if we make a plane, a vertical plane, like that, and then we draw a circle, from this point here, oh, no, sorry, an arc by 3 points, from this point here, this is it's an arch. If I go into the details, the radius is 20 meters. So 20 meters, 20 multiplied 0.25, oh, sorry, divided by 2, 2.5. Yeah. So I have calculated the pretension of the membrane, and it came out 2.5 because I made 20. It was a bit more than 20. Let's see. The radius is 20.42. So 20.42. This is the radius. Multiplied 0.25, the internal pressure, divided by 2 makes 25.5. There's something not really correct here, maybe where I made a mistake. .25 is okay. Maybe I didn't get the middle of this. Anyway, this is the formula. You can check it. This is a homework. You can check this if you do it correctly. Maybe I did not get exactly the center point of this. If you do it exactly, you should find that. No, sorry. Something that I forget to say. Again, the number of the pre-stress that we find depends, if you remember, on the number of iterations. So more iterations we make, more accurate we will get to the pre-stress. So I have used 5 iterations. Maybe if I use 10 and I run again, say plots, No, it's always 3. So we just found out that this is the correct value. So we should find out that this should be exactly 3 kilonewtons per meter priestess. Okay, maybe this can be a check, your homework, check that this is correct.
Maybe it's just a kind of approximation because 2.5 is kind of 3. So maybe you need to increase your.
Yeah, but between 2.5 and 3, it's a big difference. I think I made more a mistake on the radius.
Yeah, it might. Yeah, looked like, yes.
But we should find, if you do it correctly, you should
Mhm.
find that the balance is perfect.
Mhm.
Okay, let's go ahead in any case. And let's say that we want to do an inflatable cushion. If you remember, I have made a copy paste before inflating this membrane. I have made a Ctrl+C. I have a copy. Now I'll do Ctrl+V to paste it. The layer 0, my mesh is in this layer 0, and I will generate a tensor group out of that membrane. And you see that I have.
Excuse me.
Tell me.
Yeah.
No, I have made a copy.
Excuse me. I have a question. May I ask?
Yes.
Sure,
Yes.
go ahead.
Yes. I'm curious about the pressure number from the corner to the top of the shape. It shouldn't be differ from the corners to the center of the shape, or it should be equal in the all parts.
This is what the software solved. If we look at the priestess, you see that there is very slightly, when you see these different colors, it
Yes.
means that these are not really the same. I mean, they're different at a certain point, but almost it's a constant pressure. The software has found out this. This is a minimal surface. No, it's a bubble soap.
Yes.
And the reason why we use these form finding methods is to find out a shape where the priestess is exactly, in this case, constant, so a minimal surface.
Okay.
We see these slightly different colors, but since we are reading here 3.000, it means that here the value is not really 3.000, it's 3.00006 or something like that.
Yes.
That's why we see these slightly different colors.
Yes. Thank you.
But here it's completely green.
Yes. Thank you.
Okay, I have lost my flat mesh because I made a copy paste to go into Rhino. So what will I do? I'll do a trick. I will do a trick. Clearly, why I want to do this, I will explain you why I need to make. I want to make a copy of this. I want to make a copy of this membrane, but if I pass the same membrane, they will merge together. For the simple reason that these points, when I pass a point in the same position, the points get merged together. So if I make a copy of this membrane, of this layer, and then I pass it again, they will get merged into a single layer. So I need to copy something different. But we can do this. Look, I will make a trick. I will make a copy of this membrane, Ctrl+C. Now I am doing this for making a cushion. I will go into an inflatable and I will change the pretension to 0.1 and run the form finder. So you see, now it's flat. Now, if I do Ctrl+V and I put my tensor group inside, now I have 2 layers. They do not collapse anymore because I have moved the previous one. So now we have 2 layers. I will call this one here the bottom layer. And the new layer, I will call it the top layer. And I will just drag it inside the inflatable. Now, if we go inside the inflatable, we see that they are not correct. The order of the layers has to go from the top to the bottom. So I get this one and drag it over the top, over the bottom, and we have inflatable top layer, bottom layer. Now, if I double click on the top layer, let's change the color to red so I understand. I click on the bottom layer and I change the color to green. So, okay, I see that the top layer is red and I see it red from the top. But if I click on the bottom layer is transparent. When we see a mesh transparent, it means that this is the negative side of the mesh. A mesh has two sides, a positive side and a negative side. The positive side, you see it in the color. The negative side, you see it transparent. So we need to flip the bottom mesh upside down. So I select it. Then here we have a tool, flip. I recall flip. Now I see it green. So red and green. Okay. I click on the mesh. This is 3x3 with a pre-constraint. So that was the previous layer. Let's click on the top layer. And I will set this again. Pre-constraint. I will leave the pretension to 1x1. Let's go to the inflatable now. Now the inflatable has one chamber, and the chamber is made out by the top layer and the bottom layer with a pretension of 0. Let's put 0.3. We run the form finder. That's it. Clearly, we see here that the bottom layer has a precess of 3 kilonewtons per meter. So the curvature is quite lower than the top one, where we have set up a precess of 1 kilonewton per meter. Okay. So quite an ugly cushion, but this is how you can manage to change the curvature of one layer compared to the other one. Now let me change this to 2, just to, and we run the form finder again. Okay, so this is a quite huge ATFE cushion. Clearly, if you want, you can add the layers. If we want to add a middle layer, we can add a new layer. Let's give it a try. If I Control V, we have the mesh inside 0, and I input it as a tensor group. Okay. I will set this as the middle layer. If I run a form finding, clearly the middle layer is not inside the inflatable. So if I hide the inflatable, my middle layer is completely flat. No, that's why I run a form finding. Remember that the internal pressure, only the inflatable applies pressure to the meshes. This mesh here, the middle, the one that I call it middle, is outside the inflatable. So has no pressure. Running the form finding, it just became flat. So it's a completely flat membrane because it has a pretension. Now I want to put this middle layer under the top layer. So I just drag it over the top layer. Like that. Okay. And now we have the inflatable, the top layer, the middle layer, and the bottom layer. If we go into the params now, we see that we have 2 chambers. The top chamber number 0 is made out of the top layer, and the bottom layer is the middle one. Sorry, top layer is top, bottom layer is middle. Chamber number 1, the top layer is middle, and the bottom layer is bottom. Now, for the top layer, I input a precess of 0.25 kilonewtons per meter. And for the bottom layer, I input a pre-stress of 0.25 kilonewtons per meter. Okay. So the bottom layer, this one here, we have input 0.35, and the top layer, this one here, 0.25. We run the form finder. And we see that this is the middle layer. If I unhide everything here, we have 3 chambers. If I hide the top layer, I can see the middle layer. And if I hide the bottom layer, let's give a look at the pre-stresses. So clearly, this is the middle layer, and it has a 1 kilonewton per meter pre-stress. If I unhide the top layer, and update view, the top layer, you see, it's 2 kilonewtons per meter. This is the middle layer. And then if we unhide the bottom layer, the bottom layer has a 3 kilonewtons per meter. Yeah. So this is generally how you never make an ATFE cushion so big. This is 10 meters by 10 meters. Generally, there is a limit in 3 meters width. So if this should be a cushion, it will be 3 meters. You can make it long 10 meters, but the width should be not bigger than 2.5, 3 meters. Okay. Because generally ATFE membrane, there's a limit in the pre-stress of 40 megapascal. In this case, for ATFE, we use megapascal and not kilonewtons per meter anymore, because ATFE is not a woven material. And if you want to do this, you can go here into options, and you say, look, I want to see engineering stresses. In this case, if you set centimeters and Newton, these are megapascal. Sorry, millimeters. If you set millimeters and Newton, these are megapascal. So Newton per square millimeter is equal to a megapascal. So if you're reading a paper where you see megapascal as a pre-stress, you could choose this option, and you can see that we have 3 megapascal and 0.2 megapascal. Okay. Any questions? It's a bit tricky if you want to make an inflatable. One thing that you should remember is inflatable group, layers of the inflatable. The orientation of the layers is always facing on the top. So the top layer has to face outwards, and all the inner layers have to face in the direction of the top layer. The only one, the bottom layer, has to face outside. So the only one that is inverted is the bottom layer. The reason for this is that the software needs to know how to apply the internal pressure. Okay.
Hey, I just have one question. Can you hear me?
Yes.
Yes. So if you would have, say, a square base that would hold the cushion, however, the cushion fabric wouldn't be square, but would be several pieces sewed together, how would you proceed to find the shape that it would take under pressure? I don't know if my question is really understandable, but I'm thinking, for instance, in a sailboat. In a sailboat, the sail is actually not triangle. However, it's standing on a triangle base, and when you're going to apply pressure on it, it's going to take a specific shape. And I believe for in specific applications, you're going to have longer, for instance, longer diagonal distances within the flattened surface of your cushion. And then when you're going to apply pressure, it's going to be on a square base. Is that still unclear?
I'm not really sure, but let's make an example. I'll start a new one. Let's go in Rhino here. And let's make a an inflated arch. So I will make a vertical plane, and I will draw an arch like that, and then go from top. Then I will copy this, let's say 3 meters. And now I will close it like that. So I want to make an inflatable over this one. Okay. I get this, Control C, Control V, CAD layer, and here I am. Now I want to fill this with a membrane. I'll select everything. Remember, Swan merge. Let's make 0.25. So we have filled this membrane with the mesh. Remember that we need the edges. If I click on default, I will delete these. I don't need them anymore. Let's make the edges of this membrane with this one. Apply.
Can I interrupt you for 1 second?
Say yes.
So my question, if we take this example, my question was, what if, for instance, we don't have a straight, like the base starting surface is not a straight loft between arch 1 and arch 2, but that the surface is already bigger than what the straight loft would be. So there is already some kind of sagging happening, and that the sagging would be then taken care of by the pressure applied to that membrane. So that you wouldn't start from a straight line.
It doesn't matter really.
I think I understand your question, if I may. There's two things. The first one is so he inflates it, and it's kind of like a stretch material, like what you see. And later you do a cutting pattern to generate the 3D shape. That's one thing.
Okay. Yes. Okay. Yes. Great. So I think I understood then.
You cut the pieces so that you in the end receive the shape that you designed, and you simulate. So that the mesh is kind of, you can imagine it as a slightly stretch material.
Okay.
Somehow.
Yes. Okay. But
For
however,
the form finding.
Okay. However, the ETF is not stretchable. So okay, I think
yes, that's why you design it, and I'm sure that Jerry will show later how to pattern. How to do the cutting pattern. I think this was more a bit of your question.
Yes, exactly. Yeah, thanks.
Okay. Yeah, you're welcome.
So I didn't understand the question. No, I was thinking that was, I can start also with a deformed shape. Let's say that I want to use this dome here. With inflatables, there's a problem. I have this dome. We have seen that running the form finding over an inflatable, what happens? Remember that we have the formula, the equilibrium formula, no? The equilibrium formula says, oh, let's make something different. The equilibrium formula that I show is the equilibrium between the pressure, the geometry, and the membrane priestess. Okay, so we have a formula that relates the geometry, the curvature, the radius, the pretension in the membrane, okay, and the internal pressure. Now, what happens if I want to? This is interesting. If I want to make something like this, happens quite often in the reality. I want to make something like this. Okay. Let's say that I want this shape to be inflatable. Okay, this happens in reality. The customer comes out and says, look, I want this shape here. Where is the problem? The problem is if I run the form finding, it's very difficult to find. Now, this is simple because it's a radius, but think at something more complex. I need to find out the correct relationship between pre-stress, internal pressure, and geometry, because they're all related. What we can do is this. I can generate out of this shape, I can generate a mesh. I can go here. I generate a new group. This is a surface, and I can say generate a mesh out of this surface. Okay. So I have generated my mesh. I don't need the surface anymore. And now again, we add an inflatable, and we put the membrane inside the inflatable. Oh, I need the edges, so generate edges. I put these edges to be again beam, linear, fixed, and whatever it is here, just to fix the edges. Now I want to run the form finding, but I don't want to change the shape. Let's say that we have in the params 0.25 pressure. Okay. What we can do, if I select the mesh, I choose the material. Here, instead of form find deformable, we can set that it has to be stiff deformable. Clearly, when we use stiff deformable, we are telling the software, look, I don't want to find the shape. I just want to find the equilibrium between the internal pressure, the pre-stress, and stop, the pre-stress and internal pressure. So clearly here, we should set the amount of pre-stress near the real values. Now, I don't know which are the real values. We can calculate them clearly because we know the radius and the pressure, so we could calculate them. I will just put 4 and 4 here. I'm just guessing at this moment because I want to do a stupid thing. Let's put the wipe direction in this direction here. Okay. Now, what we have done, we are using a so-called stiff form finder, or at least we are using the analysis. When we run the analysis, we're not really doing a form finding. We are doing an analysis of an internal pressure and the pre-stress in the membrane. Let me save. And let's see what happens when we run the form finder. Clearly, you see that here, the options have changed. It's not asking me anymore how many iterations. It's asking me the accuracy of the analysis. I will start here with 25, and later I will explain you all these nice parameters here. But now he's doing another thing. He's doing a structural analysis because we are balancing the internal pressure with the pre-stress in the membrane. But now the geometry will not change so much because now he's using the real membrane. I mean, we are doing an analysis with the real membrane, and we can see the final shape here. If I go here into response, form finding, and the final shape, I get the deformed shape. And this is the real final shape. You see that we have here displacements of 8 millimeters, the red. So the shape has changed slightly to balance. But if we look at the pre-stresses, these are the stresses in the membrane. And you see that here we have blue, 3.86 in the wipe direction. And here we have 3.90 in the weft direction. So here we have done a different thing. We have designed the shape. We have input the internal pressure, and we have not used the form finder. We have used the structural analysis to find the balance between the internal pressure, the stress in the membrane, and using the real membrane material. Okay. If I change here, instead of stiff deformable, I set this to be form find deformable, and I run the form finder. Yeah. Now it has not changed for a simple reason. Why it has not changed in the shape? Because the pre-stress, you remember that I have set the pre-stress here 4 by 4, but after running the structural analysis, the software has calculated the real pre-stress for me. When I run, if I don't know which is the final pre-stress, and I put 1 and I run the form finding here using the geometrical form finder, the balancing form finder, this is what happens. So you see the shape has completely changed because the balance between the membrane pre-stress and the internal pressure wasn't, I mean, I have put it without calculating it. So it become a balloon. Okay. Okay. Let's start a different topic. You remember that the most important thing when we're using when we are generating a tensile structure, at least inside this software here, the difference between stiff deformable and form find deformable. Why we have these two options? Let's say that we want to generate. Let me go back to Rhino here, and we want to generate an I-par with the steel now. We want to add to the I-par the supporting steel. So I will make again my base 10 meters by 10 meters. Remember the layers. So I go into my layers, and this is called base. Then I make a new layer, poles, cables. Okay. Into the poles, I will draw a vertical pole here, 3 meters. And then I will copy it here. Then in the cables, I will draw 2 stay cables here. Okay. And I will copy them here. And then let's make another one, links, so I can show you how to make also fixed links. .5. Okay. And this one here is bounding. So what we want to do, we want to design this I-par. Okay. Let me draw the boundary. We want to draw this I-par. And we wanted to have these 2 turnbuckles here, 50 centimeters long, and a pole with 2 stay cables on these ends here. The first thing that we have to do is to, at least for beginners, to generate the membrane. Now, if we look at this, tensile structure, what part of this tensile structure is unknown from a geometrical point of view? Well, the membrane, I don't know the shape of the final membrane, and I don't know the shape of these turnbuckles, the direction of these turnbuckles, because they follow the reaction force in this point. So these elements and the membrane will be flagged as form-fine deformable for the simple reason that I want to find the shape of these elements. If we look at the pole and the cables here, there's nothing to define here. The geometry is defined by me. I have designed the pole, the vertical mast, and the two stay cables, no? So you can think this as a constraint on this point. So these elements are stiff deformable. I don't want to find the shape of these elements. I know the shape of the elements. Clearly, they belong to the overall geometry, but I don't want that they go into the form finder. Let's get the boundary first of all. We import the boundary as a CAD layer. So first of all, I want to find the shape. You select these elements, Suat merge, let's make it 0.35. Okay, so we have generated this mesh. Remember that we need the boundary edges of the mesh. So we recall the tool, all mesh boundary. 60 degrees, I have a 60 degrees here, it seems to work fine for this. You click on apply. And now we have the membrane and the edges of the membrane. We double click the edges of the membrane. What we want here, we want cable elements. They have a non-linear behavior. They are form-fine deformable, yes, because the cables will follow. I don't know the shape of the cable. They will follow the membrane. And then you can choose a cable, in this case, 16 or 10 millimeter cable. And then we have to input the pretension of the cable. Clearly, the sag of the cable will depend, it will be related to the pretension. I will put a 10 kilonewton pretension in the cable. I double click on the membrane. The membrane is, I want a precess of 1 kilonewton per meter and a pre-constrained Ferrari. The last step, you remember, we have to set the warp and the weft direction to this membrane. In this case, if you remember the previous lesson, this is an IPAR and the main stresses go at 45 degrees. So I go into the UCS x-axis. I click on this point here and then on this other one up here. And we have that the plane goes at 45 degrees. Right click on the mesh, warp weft mapping, and the XZ plane is the warp plane. Okay, let's save. Practically, we are doing again the IPAR that we did in the first lesson. We can run the form finder. Remember that when you have no steel, you can run this stiff form finder. Form find stiff means every stiff element becomes fixed. So error in form finding. Error in form finding. Because I have set no restraints, you see all the nodes are all green. They're all free. So clearly there are no points fixed. So the membrane has no way to find the shape. We need to fix some points. In this case, I will select the 4 corner points. And we will fix them. Run the form finder again. And we have the shape. So if you're happy with this geometry, we can go ahead and add the steel. If you're not happy, for example, the sag of this cable is too big, before adding the steel, it's better to find the correct shape. I will add a 20 kilonewtons for these cables and run the form finding again. Okay, so now the sag is smaller and I prefer this shape here. what I want to do is to add the links. If I go here and I select, I will do it one step at a time. But clearly, when you get a bit more experience, you can do everything in one step. I want to add these links. Control C, Control V. I will add them into a FEM2D group. Remember, a FEM2D group means any line becomes a structural element. And I have these links here. Now, if we look in wireframe mode and we activate the nodes, clearly this node that has been restrained is not restrained anymore. So I select the two restrained nodes, and these have to become free. The two end nodes of the links now have to become fixed. Okay, we have added these links. But if I click on the links, we have to set the properties. These are cable or truss. I will set it to cable. They are nonlinear. They are form-find deformable. I want to find the shape. I want to find the orientation of these links. I will put them as a cable 16. But now there's another option that we have to set. We want to constrain the length of these elements. I don't want that the length of these elements change. Here we have an option here. Fix current length. It's a button. You click it to true. And then you deselect. What happened is that, you see, if I go back, the fixed current length is set to false. The reason for this is that the length, the fixed value now is set to 0.5 meters. We have used this option. Think that you want to set, you have 100 links, all with a different length. To set the constraint, you should go here and write down for each of them the length of the link. It would take you hours to do that. Clicking on this option here, the software reads the current length and writes the current length into this slot. So the fixed length is 0.5 meters, and the element has a restraint of fixed length. When you do this, we have activated a nonlinear option. A nonlinear option means that to find this, if I run the form finder, the number of loops, we have to increase a little bit the number of loops because the software needs more time to relax this shape. I will set it to 20. You run the form finding. It didn't find the shape. Let's set it to 10. Oh, what's going on here? Oh, yeah, sorry. Y is not able to find because if we go here, the initial pre-stress is 0. Clearly, the software, in this case, he has started. The first step is using the current pre-stress of the link. The current pre-stress is 0, so this link practically has collapsed. We have to put here, I don't know, 10 kilonewtons as an initial pre-stress. Let's run the form finder again. Okay. If I click on this length, he's telling me here the actual length, 0.5 meters. And you see that the direction of the link follows the direction of the membrane. Okay. Now we have added,
Sorry.
Yes.
Two technical questions.
Yes.
The first one, does the software automatically recognize that it's linked? So your turnbuckle, you just copy paste it, but you did not attach it to the membrane. Does the software immediately recognize that these two things are
Yes.
connected?
Exactly. This is a general rule of the software. All the groups here, you see that we are generating all groups. All these groups have what we call a node pool. They have their own nodes. When two nodes in options, preferences, when two nodes are inside the welding persistent, in this case it's 1 millimeter, they are merged into one node. So in this case, the link and the membrane share this node, that are exactly in the same position. So when I run when we run the form finding on the analysis, the software checks the node positions. All the nodes that are inside the tolerance of 1 millimeter become one node, and all the elements are attached to that node. This is nice because if you want to delete a group, if I delete this link group, the group and the nodes disappear, so I don't have to take care of the nodes. And clearly, I am not deleting this membrane element here because this membrane element has its own node. Okay.
Okay, that's first question. Second question, you kind of like rotated the UV by 45 degrees because you said warp and weft is following these directions, the main stresses.
Yeah.
Since this is a kind of symmetric plan view,
yes,
what would happen if you choose it to be 45 degrees? Because I initially thought you would activate when we think in a cable net way, you would always activate two cables in parallel instead of one cable for warp and weft. So both are responsible for warp and both are responsible for weft. So what would be the difference, or is there a kind of like bug?
I lost you here. I mean, here we have said that this is the warp direction. When you do this, what happens? We have set a plane, a vertical plane, going from this point to this point upwards. The software gets this plane and cuts all these triangles with this plane. So each triangle is cut with a plane parallel to that one. Now, I get a plane parallel to that warp weft plane. It goes through this triangle, and the intersection between the plane and the triangle defines the warp axis. Okay, we have a plane and a triangle. The intersection between these two define the warp direction. The triangle has a normal vector. The cross product between the normal vector and the warp direction defines the weft direction. So each of these, the warp and the weft are always at 90 degrees.
So what we see here as a mesh is not representing warp and weft?
No. To see warp and weft,
that answers the question.
To see warp and weft, you have to go here and you have to look at the axis. This is warp and this is red, green, warp, weft. You see here, all the red arrows are pointing in that direction. Okay. So warp and weft.
Okay, thanks.
You're welcome. Another thing important, since we are looking at these axes, if we look at a cable or a beam element, you see that even on the linear element, we have three axes. For the linear elements, the axis number one, that's the X axis, is the axis of the element, you see. The other two, axis number 2 and axis number 3, define the cross-section plane. Okay, so when we apply a cross-section to a beam element, the extrusion will be in axis 1. And axis number 2 and axis number 3 will be, if I go here and I choose, for example, in the profiles, I get an E profile. The X-axis here in the E profile will become axis number 2 on the profile. And the Y-axis will become axis number 3. So if I put this E profile, let's do it. I get an E profile. Maybe I have it already here. Yeah. Let's get an E profile. I select this element. Remember that this is axis number 2 and axis number 3. I change the cross section to be the E profile. If we look at 3D now, let's zoom and change the color. you see that the E profile, the axis number 2 is the x-axis of the profile, and the axis number 3 is the y-axis of the profile. Huh? So when you generate beam elements and you know how you want to place the beam element in space, you should remember that axis 2 and 3 define the position of the cross section. And clearly here, in the properties of these, we have the angle. You can rotate it here, for example, 45 degrees. This is a rotation around its local axis, you see. If I select it again, I rotate it 90 degrees. We are rotating around its local axis, so we can set the direction of the stiffness where we want. Huh? Let's turn it back to the cable. I take off the axis. Okay, so we have added the two links. What we want to do now is to add the mast and the cables. So we will select these, Control C, Control V, and the cables FEM2D, the poles FEM2D. Clearly, remember that in the previous form finding, we have fixed this node. This node now is not fixed anymore. It's not fixed anymore because we are going to link this node to this pole and cable, and the same on this side here. So we set it to 3, and the bottom nodes will be fixed. Okay. The properties. Let's go to the cables. I select the cables. These are stay cables. I don't have to do any kind of form finding, so they are cable elements. They are nonlinear. They have a nonlinear behavior. They are stiff deformable now. These are real cables. We set up a cross section. And since these are stay cables, clearly they will have a pretension, but I don't know which will be the real pretension. To add stiffness to the form finding, we set up here an initial pretension, for example, 10. The real pretension will come out after the form finding. So after the form finding, I will get out which will be the real pretension to keep all this in balance. Let's double click on the poles. The pole is a beam element. Remember that beam elements, you should always use linear behavior. We have also a nonlinear behavior, but nonlinear behavior, the pole becomes very flexible, so it's better to use a linear behavior. They are stiff deformable again. The beam with the two cables are stiff deformable. And here I want a pole. This seems a bit small. No, it's okay. And we want a pole. Now, there's one thing to say. Clearly, we want it to have a rotation on the bottom, or if you want, we want the beam, this mass, to be pinned at the bottom point. Okay, we don't want bending moments here. How can we do this? If you select the pole, you remember the axis direction, the red arrow. The red arrow tells me which is the first point and which is the second point. In this case, the arrow goes from bottom to top. So bottom point is bottom point A, and top point is point B. The same for this one here. The red arrow goes from bottom to top. So if I select these two poles here, we have end restraint A and end restraint B. The end restraints, in the tables, we have the beam restraints here. You see, we have different restraints. These are You can make any restraint you want, but this is the connection between the beam element and the node. Okay. If we look at the pinned YZ, remember that YZ, the local YZ for the beam, is the cross-section axis, axis number 2. Axis 2, 3, or call it 2, 3, or YZ on the beam element. If I look at this one here, we can see that it's the movement is fixed. These are local movements. And the rotations, only the rotation around its local axis is fixed, but the rotations around the local axis Y and the local axis Z is free. What does this mean? Let me make a sketch. If I have a beam has 3 local axes, axis number 1, axis number 2, and axis number 3. By default, a beam is connected to the endpoint, is fully connected. A beam has 6 degrees of freedom at each endpoint. Which are these 6 degrees of freedom? It can, this point here can move. Let me draw it bigger. This is the endpoint of the beam. A beam can move in this direction. These are the 3 axes of the beam. Red, green, blue. This is green. And this is blue. A beam has these 3 axes at the end. So it can move this endpoint the endpoint of the beam can move in its local axis direction, the red arrow, can move in the green direction, and can move in the blue direction. Then these are 3 degrees of freedom. Then it can rotate around the red axis, it can rotate around the green axis, and it can rotate around the blue axis. These are another 3 degrees of freedom. So each beam at the endpoint has 6 degrees of freedom. By default, these degrees of freedom are totally fixed. So the beam follows the point, follows the node. We can change this behavior using these tables. You see, we can release one or more than one of these degrees of freedom. So basically, if we go back to these 2 poles, we go into restraint A is the bottom point, and we want it to be pinned YZ. We want it to rotate around the green and the blue axis. They have to be free to rotate. Okay. Let's save. And now we can run the form finder again. Now we can understand the difference between the stiff form finder and the normal form finder. If I run the stiff form finder, this one here, the stiff form finder, all the elements that have been flagged as fixed will stay, have been flagged as stiff deformable, will stay fixed. So it's like these elements will fix this node automatically. Basically, all the stiff elements are inactive. They just fix the membrane. And this is what we have done in the previous form finder. Okay. If we use this other form finder, this form finder here now is different. This form finder will take into account the membrane and the steel. You see, we have 2 options here. We have an option for the normal form finder, and an option for the Newton-Raphson analysis. Generally, you can leave these options as they are. If you have modeled correctly the model, they will run analysis and they will converge. So we have done the form finding. Clearly, nothing has changed. The shape has not changed. But now, if we go into the plots, into the response, form finding response, first of all, we have the option to see the deformation. You see that the final shape is this deformed shape. The real shape, this point here, under the precess of the membrane, has moved by 0.06 millimeters. If we look at the reaction forces, you see that we have that the pole has a reaction force of 44 kilonewtons, and the cables have a reaction force of 22 kilonewtons. So now the forces are on the ground. Here we have 19 kilonewtons. And again, the precess has changed. If we go and we look at the membrane precess, we see that the precess has slightly changed. Remember, it was 1 kilonewton per meter. When we have run the stiff form finder, it was 1 kilonewton per meter. Now it went down to 0.72 here and 0.5 here. Why this? Because this point has moved slightly. So the membrane has lost an amount of pretension. Okay. Is that clear? I mean, we had a perfect pretension when these 2 points were totally fixed. Now, running the form finding with the steel has moved slightly, so the membrane has lost a small amount of pretension, and this energy is going into these into the poles and the cables. And if we look at the cable, remember I have put in the cable a 10 kilonewton precess. If I click on this cable, the real precess is 24 kilonewton. If I go here into the pretension, oh, it's 10, but the real pretension is 24. Okay. The real pretension, we can look at it. If we look here, we go into the beam cables, axial forces. We see here that the pretension of this cable for the form finding step is 24 kilonewtons. Okay. So practically, if I have to build this, once we have made all the patterning and we have built the poles and the cables, we have to go here to these cables, and with the device where we put in pretension cables, we have to reach a pretension of 24 kilonewtons. Okay. Any question? No.
Yes.
Got scared? Yeah, tell me.
Since the angle between the membrane, like let's say the 2 edge cables of the membrane and the 2 suspension cables for the pole are the pole is not in symmetry. It's not in the bisector of these 2. So it should have. I mean, of course.
Oh yeah, I made them. I made them. I did not make them really symmetric. I made them a little. Yeah.
Yes, but what would happen if I would like to find a position where this is in balance?
Sorry?
Can I use the form finding for this too? So I'm saying that we started with the column, with a pinned column in a vertical position. But the angle, so the column is not in the bisector of the membrane and the stay cables, or the suspension cables of the car. So the column is loaded a bit asymmetric, let's say. So it's getting something like a moment, even so it's pinned.
Oh, not
Can
moment.
I find a
It's
position?
getting a moment. Yeah, it's getting a moment.
It's not a moment. I know. Yeah.
it's no, it has a moment. No, if we look at the bending moments, it has a moment. You're talking about the optimal position. If you
Yeah,
look at the bending moments, no, it has no moment, this one. Yeah, it
but it
cannot
will
be done
buckle.
directly because, yeah, finding the optimal position
Yes,
of the cables and the beam. I mean, it's not so difficult, but because here you have a reaction force that, depending on these cables, but more or less generally, it's in the direction of the membrane here in the middle. So it's clear that if I have a single force, the angles, the perfect angle here, there are many different angles, but finding the perfect angle maybe is this post should be slanted here, going inwards. The problem is, what is the best angle? I want to minimize the dimension of the cables. I want to minimize the area of the pole. I mean, we should define which is the goal to find the optimum. So if I want to minimize, in my experience, what really happens is that you have a lot of constraints on the ground. I mean, what happened in the reality is not that you want to minimize this. You don't get really, you don't save so much material generally. What happens is that we have constraints on the ground. Maybe I don't want to go. I have a swimming pool. I want to go far away from the swimming pool, or something is happening on the ground. So I have to move these cables in some place. So it's really difficult to find out an optimum in that case. You have some kind of constraints on the ground, you know? And what generally happens when we design something is that you always have constraints. So you have to, now this is nice to design an iPi perfect like that, but when you're going to do a real project, you have these constraints that at the end they are good because the constraint make you find out a nice solution. No? But yeah, we cannot really find the optimum doing this. We have to do some calculations, or in Grasshopper maybe we can do it. So that would be the next step, show how Grasshopper works. So this is all clear. If we look at this is the weft stresses. And clearly they're not symmetric because I have designed these cables in an unsymmetric way. Okay. So I think everything is clear. I hope so, at least, by merging a membrane and the steel part. The steel part, we flagged the steel part as stiff, deformable. Okay. Stiff, deformable, and the membrane as form-fine, deformable. What happens is that the software performs two steps. It runs first the form-finding step. After the form-finding step, here we have a reaction force. Then everything is merged into a single model, and a stiff analysis, a nonlinear analysis is performed, where clearly we want everything in balance. And so we end up with reaction forces on the ground or in the fixed points. The membrane changes slightly the pre-stress, and we have our initial shape. So from this shape, we can apply wind loads, snow loads, and whatever we want, and run structural analysis. Okay.
One question. When you say non-linear, is it geometrically non-linear or materially?
Both.
Or both?
It's
Okay.
both. When we run a nonlinear analysis, geometrical because displacements, we have large displacements. The membrane goes under large displacements. And then the behavior of the cables and the membrane is nonlinear, material nonlinear, because they go slack when they go in compression. So they have no stiffness for compression. They have stiffness only for tension. So material non-linear material and non-linear geometrical non-linear and material non-linear.
Okay.
Okay.
Thanks.
You're welcome. Okay. If everything is clear, Let's go to the next step. I want to remind you something before going to the next step. Remember that the model is made out of layers and groups inside layers. Remember this, no? If I make a new layer, I can call it mem. You can drag a group into a layer. I can make a new one. I call it BM, and I can drag these into my BM. If I want to make a copy of this structural part, remember that you could copy only groups. For example, if here I hide my geometrical elements and I do something like this, I select. Then I go into the CAD tools and this is a copy. When I call the copy command, it's asking me to select objects. You cannot select FEM entities anymore as a post selection. We can select them only as a pre-selection. So now I just right click and it's asking me the source and the destination. So I can make a copy out of these. Okay. And you see that all the groups have been cloned and all the edges have been cloned. So I have made copies of those, but all the group has been copied. So even if you select only one element of a group, all the group will be cloned. The same happens if you use rotate, scale, whatever it is. Okay. So we have groups. The organization of a model is made out of layers, groups, and each group has some subgroups. The tensor group has a tree mesh subgroup, and so on. Nice. Let's go ahead. What we do now, we want to design in a parametric way these tensor structures. I mean, I am lazy and I don't want to use the software. I don't want to use Xcube inside the software. We want to use Grasshopper. You know Grasshopper? Yes. So if I load Grasshopper, first of all, when we want to use Grasshopper, you first have to run Xcube. Then you have to run Rhino with administrator rights. Run as administrator. If we don't run it as administrator, it will not work. So once we are inside Grasshopper, you can see you will find out the Xcube toolbar. You see that it's quite large. There are a huge amount of features. And now we will see how to use them. Everything becomes quite simple once we know what happens inside the software. First of all, let me check the query tools. I will open my iPad. The easiest tools to use are the get tools. If I go into the get tools, we can use the tool get group list. If we use the get group list tool, you see here what we see is the list of groups that we have generated. I go back to my Xcube. Then we have the get layers. These are the layers that we have generated. Now, we have also the get group. If I connect the group, he wants the group name. So if I connect all the groups to this group name and I say update, here my membrane is inside Rhino now. The get groups has got the meshes from Xcube, the curves from Xcube, and all the information to these other node elements. So basically, I have got all the information out of Xcube. Now, what we want to do is this is parsing geometrical information. What we have now, there's a lot of information for your brains. What we have in these tools, we have the tools to generate information. Here we can generate information. Then we can get all the geometrical information and the properties of the elements. Then we can apply loads, we can generate loads, and then we can run analysis and post-process data. Okay. Let's start easy. We start making a new job. If we want to start making a new job, the first thing that I suggest to do is we go here into the global panel and we have templates. If we look at the templates, you remember these are the templates that we have used when we started a new job. It's always a good thing to start with a template. For a simple reason, if you start making, in the beginning you start simple, but if you go on and you make really complex models, we want to be sure that we start always from the same point. And so starting with a template is always a good starting point. Clearly, you can make your own template if you want and start with your own template. So I want to get this template. We go into Xcube, and from the global, we recall the load file. Open file. Open file. We choose one of these templates. I want to start with template number 1. With template number 1. And then I want to save. So when I start like this, I'm sure that I am starting always from the same position. Okay. When you see here, you must be sure when you save this one here will save the file. You must be sure that the directory work exists. So I go into my C. And I be sure that I have a folder. A lot of folders here. A new folder, name it work. If the folder doesn't exist, they will not be able to save it. I turn back to my Grasshopper. Now, if I run here and I go back to Xcube, you see that the name of the job is C work my model XF. Okay. Is that clear? So I am just starting to do, and I start a job. I want to be sure that I start from the same position. This seems something a bit stupid, but it's not is really stupid. When we start, if you try to make a real complex thing in Grasshopper and you don't start from the same position, it's quite often that you get up different models and different results, and you don't know the reason. And the reason is that maybe the environment is different. Now, let's say that we want to generate a tensile structure from inside Grasshopper. I will not make a parametric one in this moment. I just want to make a simple one, and then we'll see how to make it parametric. It depends on your experience inside Grasshopper, but it's not so difficult. Anyway, the first things that the tools that we use to generate tensile structures, all these tools here. We have linear element, mesh element, and point element. What are these elements? Let's start making the mesh. I will start from here. I will make a surface out of these 4 points. Surface from edge curves. Okay. I will get this surface, go into the parameters. I will get a surface, brep, set one brep. Okay, so I have here my surface. Yeah, clearly this is a NURB surface. We go into the mesh tools, and we have the tools mesh brep. This is, let's hide this. This is my mesh. Clearly, we have options to remesh, to change the settings of the mesh. But inside Xcube, we have a tool. In the tools, we have a remesh tool. The same mesh tool that we have in Xcube. So I wanted 0.25. And the mesh. Let's hide this one. And you see that we have again a mesh 0.25 by 0.25. Okay. This is the mesh inside Grasshopper. We want it to become a tensile structure. To do this, we will use the tool mesh set. What is mesh set? Mesh set is this component here. It wants a mesh as an input. And then we have the priestess in the warp and in the weft direction. Okay. The priestess in the warp and in the weft direction. The pressure, if we want to make an inflatable, we can apply a pressure, but this I think is a bit obsolete. And then the warp plane. You remember that we have to set a plane for what is warp and what is weft. Let's go here. We can go into the vect plane. We can make a construct plane. The origin is okay. The x-axis, I can get. There are many ways to do this, but I'm lazy. I'll just draw a line here and say vector by 2 points. This one here. This one here. So this is my x-axis. And my epsilon axis is simply vector unit z. So you see this plane here, and I would input into the warp plane. The seed is the material. Remember that we have applied for the membrane and for the beams, we need to apply a material, a cross-section or a material. And where do we get it? Well, we go back to Xcube. In the get, we have get seeds. if you get a panel and plug the seeds, these are all the seeds we have defined in the template. And here you understand why it's important to use a template. If I make my own template, I fill it with all the materials, the cross sections I want to use. So when I start this project, the seed list is always the same. Figure out if you make a parametric model and you use one template, then you go back, you use another template, because now what I am going to do is I am going to reference, for example, for the membrane, I need to reference seed number 6. Okay. So I am going to reference seed number 6. Think about it, that you have made a huge, beautiful project with working for 1 week, making a complex parametric model with all materials, seeds, and so on. And you load a different template where at number 6, you don't have a material, but you have a cross section or a steel profile because you have just used a different list. Clearly, you go crazy because nothing works anymore. The reason why starting from your own template will make you in a safe place where everything will always work. Now, what we do, we get this seed and we plug it into the seed. And now we have what I call this is a mesh enriched with data. It's just a mesh, but has all this data over the mesh. Okay. Let's make a bit in order this. This is my membrane. Let's say that we want to generate now this membrane. Remember that the membrane, we don't have the edges. So before running any form finding, we have to generate the edges. Now I just want to show you how to generate the membrane. This is just the mesh. If we go into the iXCube toolbar, we have the generate. We can generate a FEM2D group, a node group, a shell group, and a tensor group. If we go into the tensor group wants a mesh set, so I just plug in the mesh set. The name of the group, this is my iPad. And the name of the layer, this is my membrane. You can just click on update. That's quite big. If we go back to iXCube, we have generated our mesh. Okay. One thing that I see that it's flipped. The positive side, remember that generally you want the positive side on the top of the membrane. The positive side for 2 reasons. The first one is when we apply loads. When we apply loads, the positive load will push the positive side. And then when we generate patterns, the positive side will be the top of the panel. This one. Generally, we pattern looking from top. So if we go back here, I can say here in the flip, I will use a Boolean input and set it to true. If I generate the model again, is working now. You see that the membrane is on the correct side. Okay. Fine, we have generated the membrane. What we want to do now, we want to generate the edges of the mesh. Okay. How can I generate the edges of the mesh? Well, this is a bit more tricky. I would like to make them I would like to make only 4 edges, but this takes a little bit time. In this moment, I will make all the edges in single pieces. If we go into the mesh tools, we have a mesh a deconstruct mesh tool. Deconstruct mesh, if I input the mesh into the deconstruct mesh, oh, sorry, not this one. Oh, mesh edges, sorry. If I plug in the mesh into the mesh edges, we see that this tool here gives me the naked edges. So if I plug in the naked edges into a curve tool, these are the naked edges, the boundary edges of my mesh. So I am ready to generate the boundary cables. We can go into Xcube again. Now we will use this one here, the link set. The link set, the first input wants curves, and these are the boundary of my membrane. Then the Q is the priestess, or the first density value, and I would input here a 20. The type of the element, we can choose between cable, truss, or beam. These are cable elements. The deformability, these are form-find deformable. And then we have the releases and the up vector. I don't need these because these are cable elements. So we have a link set. We go into the generate, and we have here generate a FEM 2D group. Generate a FEM 2D group. We input the link set. The name is edges. And the layer, again, edges. If we click on update, we see that we have generated the edges for the membrane. What is missing? Clearly, I am generating these objects, I am generating them one by one. But if you want, you can make a button here. Where is it? And you can connect the button to this bay. So when I click on this one here, he will generate everything in one shot. One thing is missing, and this is the fixed points, the 4 corner points that I need to fix. So how do we generate fixed points? What I need, the 4 corner points of this membrane. Now, there are different ways to detect this. I want to make things simple in this moment. I will draw 4 points. I will go into the tools, set multiple points. Clearly, you can detect these points by your geometry, but I need to go fast in this moment. So I have 4 points here, and these points are constrained points. How do we generate this? Well, we go again in Xcube, and we have here, you see, a node set. He wants the points, and then he wants a restraint. For the restraint, we have a restraint condition. In the restraint, you find out the 6 degrees of freedom for a point. So we have generated here 4 constrained points. There is a little difference now because we will generate a node group. A node group is simply an empty group. There's no geometry inside, but it has only points. So we can fix these points to constrain the geometry in some place in space. So I will just attach a node set. I will just attach the restraints. We will call this fixed nodes. And these are nodes. I click on update, if we go back here, we have the fixed nodes. You see, we have no geometry in the fixed nodes, but if I go into the FEM-tools and we unhide the nodes, you'll see that we have 4 fixed nodes at the corner points. Okay. We can just, I would run the form finder from here. Error in form finding, what's going on? The priestess here. No, that's the protection. The edges. Something wrong with the edges. Nice. That's nice. There's something wrong with the edges. Where is my mistake? I did something wrong here. I think I got the wrong mesh when I generated my edges. Let me see.
Yes, you
Oh,
don't
yeah, you
have
see.
only the naked edges.
No. I have used the mesh coming from the mesh from the B-rep. You see? This is the mesh I have used it here. And this is the mesh from the B-rep. I have plugged in the first mesh into my edges. I should plug in this one here. So now I can generate my edges again. Got it wrong. What's wrong with you? I will delete this. Let me see. Hey, what's that? Let's make a new group. Let's make a new group. I don't know what happened. Let's make a new group just to see maybe. This one you like it. Oh, where is it? I lost my X cube. The server has crashed. That's why. I have only one session here. Okay, let's do this. I will delete this. I will connect this one here. And I will connect this here. I will go here and I will click on this one. So you see, I started from scratch again. And then I will click here to generate the model. Let's see what happens. Let me check my edges. If I hide my membrane, yeah, now they seem to be correct. So we can run the form finder. Yeah. That's it. Now it's working. The nice thing is that if we go into the global here, we can run the form finder from here. And again, we have the options. Number of steps if it's non-linear, and so on. So you can just run the form finder. It's telling you it's form finding now. And the form finder has converged with success. Okay. Once you have run the form finder, we can open a window from inside Grasshopper. So basically, there's no need, once you learn all these tools, there's no need to leave Grasshopper. This is a window inside Grasshopper. And we can also make Windows settings. We can plot, for example, response form finding. We want to look at the membrane stresses. We go into membrane here and look at membrane stresses like that. Okay. So basically, well, this will take a little bit time, but I think using Grasshopper, the nice thing is that we can merge all these tools with all the parametric tools we have inside Grasshopper. So we can generate parametric models and on the fly generate a tensor structure and check out if it's working. It will take a little bit time more to grasp these tools, but if you're a Grasshopper user, you can. I think it's quite easy to understand these things. A nice thing that we have here, if you go into post process, and this tool here, this tool check elements, we can recall from here the profile and the material explorer. So if one of these profiles is missing, you can generate one of these profiles or seeds, and you just click with OK. For example, I want to get a 219 millimeter into my model. So I add these seeds to the model. Okay. And then I go back to my seeds. We update, and we have these new profiles into the seed list. I know really a lot of information today. So what I suggest for your try to make an inflated cushion just to understand the feature that we were talking about, cushions, and then try to make an IPAR using Grasshopper, just what we have done here. Okay. Any questions? You got scared? No. You know Grasshopper. Everybody now knows Grasshopper, no? You never seen Grasshopper? Nobody. I don't hear anybody else ever use it. If you go onto the Grasshopper website, onto the Rhino, you'll find a huge amount of stuff to learn the basics of Grasshopper. But for anybody in the field of architecture and engineering, it's very easy to grasp. These we have vectors, points, surfaces, curves. So all things that we know very well. And then we have these black boxes that are just inputs and outputs. So after a few days, you'll find yourself to be, I mean, quite going on quite well. One thing is that it needs good planning. Now, you see me, I have started a bit messy job here. But if you plan nice, in a careful way, you're able to do amazing things. Okay. I think we have reached the 2 hours. Everybody's tired now. Huh?
May I just have one question?
Tell me.
Sure.
Yeah.
Go ahead.
Yes, I'm just curious about the optimization runs from the Grasshopper. How can we reach the geometry, or is it any component inside the IceCube that record the alternatives of the optimization that comes from the IceCube?
No, don't. Yeah, but how can we do it? We have seen here, for example, that if I put all these options together, we can generate a model if I go here and I connect this one to this one here, as soon as I click here, run, he generates the model. Okay. Now think about it. You have a tool. We're changing parameters. We can have some parameters. We can generate the model out of a number of parameters.
Yes.
Okay. There's no optimization tool inside Xcube. Xcube, his role is to run an analysis and give you a response. If I go here into the Xcube tool, here, for example, we have post-processing where I can get all the information about stresses, forces, energy, whatever you want. Using the Grasshopper tools, Grasshopper has different optimization tools. For example, Galapagos, where you can optimize. So basically, this is your scenario. I could say, okay, I have my input parameters, and then I generate a model, I generate the analysis, whatever you want, and I get some output parameters. And I want to optimize these parameters here. So you can generate out of Galapagos a number of scenarios in batch mode. He runs in batch mode. You get these parameters, and he generates a number of different scenarios. You get the best ones, and that's your kind of optimization. All the optimizations work like this. First of all, you need to know what you want to optimize. If we don't have a goal in mind, there's nothing to optimize. So you have to plan carefully the goal you have. What you want to optimize the amount of steel. You want to optimize the weight of the steel. You want to optimize, I don't know, something else. So you first have to set up the goal. Once you have set up the goal, we can design a procedure where we can generate models, run an analysis, get the final outputs, and optimize and get some optimization parameters. So all this can be run in a kind of automatic way. One thing that can be optimized here, for example, but this is a different question. In Xcube, we have an optimization, but it has nothing to do with the optimization I think you have in mind. This optimization here, we can generate a family of profiles. Okay. We generate a family of profiles. For example, I generate a family with 10 profiles. And then we apply these profiles to the steel framework. Then we run analysis and we ask him to make an optimization. He will find out the best profile for the analysis on the hand, looking at the stiffness of the profile. But this is an optimization based on which is the in a family of profiles, which is the best profile for that kind of analysis. Inside Grasshopper, we can make something much more complex. Okay, but it takes time. I mean, you need to know where to put your hands inside here before you doing something like that.
I'm just curious about the optimization that you had in the Xcube, and you said that it's for about the family of the elements or the
this one
material.
is for making an optimization of the profile. Because it's hardly related to if you're making a real job. Now, let me open a file here. I can show you. And then we will close here. Yeah, you see here, you have a lot of steel.
Yes.
When you're making a real job, one of the goals is to optimize the steel, because if you save the weight, you save a huge amount of money.
Yes.
Huh? So you want to make it as light as possible. But here, the optimization is, we have a lot of load cases now. If you go here, you have all the load cases for the analysis, and we want to be sure that the profile passes all these analysis, and we want to find out which is the best profile for all these load cases. So it's a profile optimization. Huh? Other
It depends on the
optimizations can be.
Yes,
tell me.
I was curious about this. This is a hierarchy of the scenario that we had in mind. We first optimize the geometry, for example, based on the nodes, and then we can use this optimization to find the best
exactly.
material, or
Exactly. I mean,
Yes.
here in Grasshopper, you make a geometrical topology optimization. You find the best
yes.
shape and the best project for
Mhm.
the project. After that, the final optimization would be optimize the amount of steel, the weight of the steel, and the amount of
Exactly.
material. Okay.
Thank you for the declaration. Thank you.
You're welcome. Okay. It's 11:12, so I think everybody's quite tired after 2 hours. At least I am.
Are there any questions left? Otherwise, we're going to close the session for today.